Hey guys, so in the first problem, the first part of the first problem, we did the brute force approach. Now this approach is just using an equation, and you're gonna see how the time for doing it is way smaller. So let's try to do it again. Remember what is the statement of the problem? Find the influence lines, reactions for the reactions AY and BY, and later on we're gonna get also for shear and for moment and for other stuff. But A and B using the equation instead of using the brute force approach. And remember, the philosophy is that you have the little moving load here. That's what happens. The load is moving, and because the load is moving, and we don't know exactly where the load is going to be, so we're going to put the load there, right there. And by right there, I mean at an x distance from the support A. And I'm gonna make that distance change from 0 to 12. And that's how we're gonna do it. So summation of moments at A equals 0, like that. Now I can do perfectly summation of moments here. This is the reaction AY, this is the reaction BY. Summation of moments at A, so you have negative 1 times x, negative 1x, plus by times 8, or 8by, equals 0. And you can get that by is going to be equal to, pass this to the other side, 1/8 of x. Now if you do summation of forces in y equals 0, you can say that AY minus 1 plus BY equals 0, or AY is going to be every single time 1 minus BY, or you can say also that AY is going to be every single time 1 minus this, 1 minus 1/8 of x, or 1 minus BY. And that's it. After that, the only thing you have to do, build your table. 1, 2, 3, 4, 5, 1, 2, x in meters. Of course, you should have here some units like meter and the denominator, so it cancel out, but this is obvious. So AY and BY. And then you start applying the equation for x equals 0, 4, 8, and 12. 0, 4, 8, and 12. Now from when x equals 0, if you're here in by, you're going to have 1/8 times 0, which is 0, meaning by is going to be 0. And if you apply this is going to be 1 minus 0 equal 1, so this is going to be 1. When you go for x equals 4 here, so you have 1/8 of 4 is 0.5, so this is 0.5. And then you have 1 minus 0.5 from here, 0.5, meaning this is 0.5. X equals 8, so you have 1/8 of 8 is 1. This is 1, and this is 1 minus 1, because this is 1. And I'm using this equation, so that means this is 0. And for x equals 12, you have 1/8 of 12, which is 1.5, 1.5, and then here you're going to have 1 minus 1.5, and this is negative 0.5. Boom, done. Well, not done, but in my case it's done, because now you have to just plot it, and we already did the plot here in the other example that we solved, but it's the same thing. So you just plot these values here, x 1.50, 1.50, negative 0.5 for 12, and then the same thing from these ones here, 0, 0.5, 1, 1.5, and that will be the influence lines. Now the use of these influence lines is going to become more obvious and obvious and obvious as we are moving through more examples, but just for the sake of, you know, the argument of being talking here, and let's say that these are the influence lines, and I want to know, listen, I need to know what is going to be the maximum possibility for a vehicle now. Let's talk about a vehicle that is passing through this road, if this is a road, to produce the biggest possible reaction at the support B, and this is my influence line. Now, if this is the vehicle here, and this is a scale, because you have to do it a scale or put the right the distances here. If I know that if I put a load of 1 here, the reaction is going to be 1.5. So if I put a load of 2, the reaction is going to be 3. If I put a load of 4 kips, the reaction is going to be 4 kips times 1.5, 6,000 or 6 kips over there. And if I put a vehicle here, where you have these 2 tires, for saying something, and every tire has a particular load, the maximum reaction or the reaction at this point will be this reaction multiplied by 1.5 and this reaction multiplied by whatever point, whatever value is that point. That's the beautiful thing about the influence lines. Now, if I ask you here, what is the maximum, where is the location of the load for producing the maximum reaction at support A? Now again, the answer there will be, it depends. And I start thinking about that right now. The answer here will be, it depends. Why it depends? Because if the car is here, in this part, this is positive. Positive means the reaction is pointing up. So obviously, in this direction or in this direction, I don't know what the direction is going to be, either of these 2 directions. Oh look, it lost a tire here. You know what this car lost the tire? Because it went beyond the 12 meters. It was here, and it went below, and it crashed. I know it's a bad joke, but I don't care. So this is free, so you have to listen to it. Okay. Anyway, if I put the car here, yes, it's gonna be positive, right? I'm gonna put the 2 wheels here. And I'm gonna do the same thing. This multiplied by this multiplied by whatever value is there in a scale. But what happens when the car is located here? Now the reaction is gonna be negative. That means that you're gonna have 2 possibilities for reaction. You're gonna have a maximum reaction in Y, a maximum reaction in Y, AY max, when AY is acting in this direction. But I know that if the vehicle is at this location here, and this is going to be trying to do that, I have to hold it somehow, because otherwise this is going to go unstable in that direction, and it's going to be a negative value, and we're going to have also a negative value for AY, which I call maximum positive or maximum negative. But this is the first example. I just wanted to give you a brief introduction on how to do this, and also a brief introduction on why you are going to be using the unit influence lines. The other part of this problem, part 3, we have to calculate the shear at the point C, and let's say the point C is a point here at the center. This is going to be my next video. See you there. Keep watching and keep learning, please.